Welcome to today's paper reading. Today's paper is titled, Contextual Position Encoding, Learning to Count What's Important. This paper, titled Contextual Position Encoding, Learning to Count What's Important, is authored by Olga Golovneva, Tianlu Wang, Weston, and Sainbayar Sukhbaatar from FAIR at Meta. The work is currently under review and presents a novel approach to position encoding in large language models. The attention mechanism is a crucial element in large language models, LLMs, enabling tokens to interact regardless of their order. To address tokens by their position encoding, P is used. However, existing P methods, which rely on token counts, are limited to token-level addressing and cannot handle higher-level abstractions like sentences. This paper introduces a new method called Contextual Position Encoding, COPE, which conditions positions on context, allowing for more general addressing such as attending to specific words or sentences. COPE has been shown to outperform traditional P methods in tasks like selective copy, counting, and flip-flop, and also improves performance in language modeling and coding tasks. The introduction highlights the critical role of position encoding in processing ordered sequences like text, audio, and code. In text processing, position information is essential at various scales, from words to sentences. The transformer architecture, which is the backbone of current large language models, lacks inherent ordering information and thus requires additional mechanisms for encoding position. Existing methods include absolute position encoding, which counts tokens from the start, and relative position encoding, which counts backward from the current token. However, these methods face challenges with token position variance and the separation of position and context addressing. To address these issues, the authors propose a new method called Contextual Position Encoding, COPE, which integrates context and position addressing together, allowing for more semantically meaningful position measurements. Figure 1 illustrates the Contextual Position Encoding, COPE, method. Unlike standard position encoding methods like relative P, which are based on token positions, COPE first computes gate values that are conditioned on the context. These gate values are then used to assign positions to tokens through a cumulative sum process. This approach allows positions to be contextualized, enabling the representation of counts for various units such as words, verbs, or sentences. COPE operates on each attention head, allowing it to attend to different types of positions simultaneously. In the example provided, attending to the last sentence using relative P is problematic due to a decaying attention pattern known as recency bias. In contrast, COPE can accurately count sentence endings and attend to position 0. The core of the attention mechanism involves a softmax operation over tokens in a sequence. This operation generates query, key, and value vectors through linear transformations of hidden representations. However, this attention operation is invariant to position information, necessitating an additional position encoding mechanism. Position encoding methods are categorized into absolute and relative. Absolute position encoding adds a vector representing an absolute position to the hidden states, either through a learnable embedding layer or a fixed sinusoidal function. Relative position encoding, on the other hand, depends on both the current token and the token being attended to, implemented within the attention layer. This can be done by adding the position encoding to the key vectors, with variations using either learnable embeddings or fixed functions. The term Q-IJ can be viewed as context addressing, while Q-I-I-J is position addressing. Despite various proposed methods focusing on efficiency, they all rely on token positions. The motivation for contextual position encoding arises from the limitations of standard position encoding techniques. These techniques fail on even simple tasks, such as identifying the last occurrence of a token in a sequence. For instance, in a sequence like YYYYXYYY, standard position encoding struggles to focus attention on the token X when it is far from the end. This is because the attention difference depends on the positions of tokens, which can be imprecise. Additionally, state-of-the-art large language models, LLMs, like GPT-4 and Llama 270B chat also exhibit basic failures in tasks requiring precise attention to sentence positions, such as word counting. These models struggle because token positions do not accurately reflect sentence boundaries. Contextual position encoding aims to address these issues by combining context and position information, thereby improving the model's ability to perform complex attention tasks accurately. In COPE, positions are determined contextually rather than by simple token counts. This is achieved by computing a gate value for each query key pair, which decides whether the key should be included in the position measurement. The gate value is derived from the sigmoid function applied to the dot product of the query and key vectors. This soft gating mechanism allows for differentiation, enabling the system to be trained via backpropagation. Position values are then computed by summing these gate values between the current and target tokens. Unlike traditional methods, these position values can be fractional due to the sigmoid function, necessitating interpolation between integer embeddings. To enhance efficiency, COPE limits the maximum possible position and extends naturally to multi-head attention, where each head can implement different position measurements. Additionally, separate keys can be used to disentangle position from attention, although this increases computational requirements. In the flip-flop task, COPE demonstrates superior performance by effectively reasoning over long input sequences and generalizing well to both in-distribution and out-of-distribution data. The selective copy task highlights COPE's ability to manage varying numbers of blank tokens and maintain accuracy on both in-distribution and out-of-distribution test sets. For the counting task, COPE shows excellent capability in tracking multiple variables and generalizes better to varying context lengths compared to other methods. Figure 2 illustrates the performance of COPE and relative P on the counting task. The key observation is that COPE significantly outperforms relative P, particularly when there is less training data available for the task. This performance gap is attributed to COPE's ability to measure position in a context-dependent manner, which allows it to better handle the counting task under data-limited conditions. The figure highlights the superiority of COPE in scenarios where the model needs to generalize from minimal training examples. Table 2 presents the test error rates for the flip-flop and selective copy tasks, distinguishing between in-distribution and out-of-distribution (OD) scenarios. COPE demonstrates superior performance, achieving a 0% error rate in distribution and maintaining a low 4.9% error rate for OD, significantly outperforming both absolute P and ROPE methods. Table 3 presents the test error rates for the counting task across different numbers of variables. The error rates are reported for 3 positional encoding methods: absolute P, relative P, and COPE. The task involves counting operations and sequences with varying complexity, from 1 variable to 5 variables. COPE demonstrates consistently lower error rates compared to the other methods, especially as the number of variables increases, indicating its effectiveness in handling more complex counting tasks. Table 4 presents the out-of-distribution (OD) generalization error percentages on the counting task. The table shows that COPE significantly outperforms the relative P method in handling longer and shorter contexts. Specifically, COPE achieves 0% error in both in-domain and OD longer context scenarios, and a 4% error in the OD shorter context. In contrast, relative P shows higher error rates, particularly in the OD shorter context, where it reaches 34.1% error. Table 5 presents the results of Wikitext 103 encode modeling tasks. The table compares different positional encoding P methods in terms of the number of parameters, params, and perplexity, PPL, on the validation and test sets. Absolute P shows the highest perplexity on the test set with 24.87, while COPE demonstrates a significant improvement with a perplexity of 23.46. Combining COPE with relative P further reduces the perplexity to 23.23, indicating the effectiveness of COPE in enhancing language modeling tasks. Figure 3 illustrates the generalization of COPE to longer context lengths. The model was trained on the Wikitext 103 language modeling task with context sizes of 10, 24, and 512. Upon evaluation on longer context sizes, COPE demonstrated superior performance, significantly outperforming existing positional encoding methods. Notably, the performance gap between COPE and other methods widened as the test context size exceeded the training context size, indicating COPE's robust generalization capabilities. Figure 4 illustrates how COPE, a contextualized position encoding method, focuses attention on abstract elements such as paragraphs and sections based on their positions in the text. On the left, the attention is shown to be separated by newline tokens, indicated by black plus signs. On the right, the attention is separated by section titles such as description marked similarly. This demonstrates COPE's ability to attend to these structural elements in a contextual manner, enhancing its understanding of the text's organization. The attention mechanism, initially proposed by Botanau et al. In 2014, did not require position encoding as it was based on RNNs. However, the memory network architecture introduced by Weston et al. In 2015 began using position encoding with attention mechanisms. This was also seen earlier in a convolution-based architecture by Contextual and Weston in 2008. The transformer architecture popularized position encoding, with Vaswani et al. In 2017 using absolute position encoding. Subsequently, Shaw et al. In 2018 introduced relative position encoding, which was particularly effective for unbounded sequences as noted by Dai et al. In 2019. Recent innovations include the use of biased scalars by Rathel et al. In 2020, fixed decaying bias terms by Press et al. In 2022, and the removal of position encoding with token counting by Haviv et al. In 2022. In this paper, the authors introduced a novel position encoding method called COPE. This method measures position in a context-dependent manner, differing from the current token-based position paradigm. This approach provides more flexibility in addressing by position and has shown improvements in several tasks. Although the study primarily focused on text and code domains, COPE has potential applications in video and speech domains where token position is less appropriate. Future research could explore training larger models with COPE and evaluating their performance on downstream tasks. In this section, the author expresses gratitude to Mike Lewis for his valuable discussions and advice, which significantly contributed to the research. Additionally, the references section provides a list of citations that offer further reading and supporting evidence, helping to contextualize the research within the broader academic discourse. Thank you for watching.